Good evening, guys. Hope you're doing well. This is going to bring us into our thermochemistry lecture, and this is one of the last topics that we're going to be talking about. So we're going to be talking chapter 6, sections 1 through 4 today, and we'll get into that in just a second. Let me go ahead and share my screen, and then I will start my slideshow. So again, we're going to be talking about chapter 6. This is the next couple of things about thermodynamics that we're going to talk about. All of the thermodynamic stuff that we're going to be talking about is going to get us into discussions of free energy, which is going to talk directly to spontaneity. So we'll talk about the thermochemistry portion of it first, and then we'll talk about some of the other parts of this. So again, nature of energy, types of energy. We're going to talk about energy changes in chemical reactions. We'll do an intro to thermodynamics, and then we'll talk about the enthalpy of chemical reactions again. So, unlike most of what we do, this lecture is almost all theory. There's not a lot of practical application here. The material is very dry. It's mostly definitions of things that we'll need to be able to work with as we move forward to talk about the enthalpy, the entropy, and the free energy, which is the last couple of things that we're going to do. There's not a lot of practice that's going to go with this on its own, but we will be looking at how we use this stuff when we move forward. You will see a couple of things like define this term, tell me the sign conventions, what is, that kind of stuff. And we'll talk about that as we move forward. But I wanted to make sure that you were aware that that's what we're going to be dealing with here. Okay? Nature and types of energy. So energy is the capacity to do work. All right, that's how we define energy. There are several types we talk about. So we talk about radiant energy, which is solar energy coming from the sun, heats the atmosphere, the Earth's surface, stimulates vegetative growth, and it creates the climate patterns. So that has the ability to do work. Thermal energy is associated with random motion of atoms and molecules. It's directly related to the temperature. Energy is a function of both the amount of material and its motion. So larger masses have a higher amount of energy. More material, more stuff that can move. Chemical energy is stored in chemical substances. Chemical reactions release during bond breakage, store during bond formation, and convert energy to other forms. Okay. We also talk about potential energy. So that's energy available based on the position of a material. We typically think about this as looking at the potential energy of something that's high up that can fall. All right, so that's a physics thing, but it has to do with potential energy that's available based on where something is located. Okay. The law of conservation of energy states that the total quantity of energy in the universe is assumed constant. Energy is neither created nor destroyed. It's only converted from one form to another. Okay. Questions, comments, problems about our definitions of energy and the fact that we don't create it, we just change it. All right. So energy change in chemical reactions. Most chemical reactions involve the exchange of heat. Thermochemistry is the study of heat change in chemical reactions. Heat is a transfer of thermal energy from a material higher in energy to one lower in energy. It's usually measured by the temperature of that material. Okay, that's usually how we measure the energy that we're talking about. Now we can define two places that we can look for this. One is something we call the system. All right, so if we're looking at a particular reaction, that's our system. If we're looking at a particular room, that's our system. All right, everything else, anything that is not our system, is called the surroundings. All right. So everything else in the universe outside of our system is our surroundings. So we can define three types of systems. We can have an open one. It can exchange mass and energy with its surroundings. A closed one that allows the transfer of heat but not mass to our surroundings. Or an isolated system where we cannot transfer mass or heat. Okay, so an open system can transfer anything. Closed system can only transfer heat, and an isolated system cannot transfer anything. All right. Heat transfer is talked about in two terms. One is exothermic, where energy is given off from the system to the surroundings. We talked about this last time. We talked about our reactants being higher in energy, or our reactants being here and our products being lower in energy. That's exothermic. We also talked about endothermic, where we have to take in energy from the surroundings to be able to get something to happen. So this was when we talked about our reactants and products having a lower energy. So having a higher energy than our products do. Okay. So energy is taken in by the system from the surroundings. Heat is a reactant. Okay. And of course, if it's exothermic, heat is a product. So we talked about, when we talked about Le Chatelier's principle, and we talked about if heat is a product, right, and we add heat to that system, i.e. we raise the temperature, then it's going to shift backwards, right? If heat is a reactant, i.e. it's endothermic, and we need that energy to make this happen, then if we raise the temperature, that's going to drive it forward, okay? So that's how we come with all of these happy terms, endothermic, exothermic, right? Questions about that? All right, if you have questions, comments, problems, concerns, anything, please let me know. Email, phone, come to my office hours, drop by my office, whatever. Let's make sure that we can get that taken care of. Now, let's do an intro of thermal. Thermodynamics is the scientific study of the interconversion of heat and other forms of energy. So we can study the state of a system, okay? This talks about the composition, the energy, the temperature, the pressure, the volume. So this is everything that we're talking about in the part that we care about, so our system. Composition, energy, temperature, pressure, volume. And we can talk about state functions. So properties that are used to determine the state of a system, regardless of how it got to that state. The only thing that matters here is the initial and final states. Volume, temperature, pressure, and energy are all state functions. So again, it has nothing to do with the pathway that I took, only my start and my finish. That's all I care about. So those are state functions, all right? The first law of thermodynamics. Energy can be converted from one form to another, but not created or destroyed. Energy has two main components that we consider. Sorry, there was a big blow and it scared me. It sounded like thunder. Energy has two main components that we consider: kinetic energy and potential energy. So kinetic energy is the molecular motion and movement of electrons and molecules. So that's the movement, the kinetic part. Potential energy is attractive interactions between electrons and nuclei, and repulsive interactions between nuclei and electrons, and between individual molecules, okay? Measurement of all forms of energy is extremely difficult to do, but changes in energy can be determined experimentally. Potential energy, U, is our measure of these. So delta U for the system has to equal the negative of delta U for the surroundings. So the potential energy change in the system is equal in size, but opposite in sign to the change in the universe. All right. If a system goes from high potential energy to low potential energy, like a stone falling off a cliff, then the surroundings gains that energy that was given off by the stone. It can be in a different form. It doesn't have to be the same kind of energy. Here, we're more interested in what happens to the system. So let's see what that looks like. Our potential energy is equal to Q plus W. Q is the heat exchange, and W is the work. All right, so the potential energy is going to be based on heat and work. Awesome possum. Heat. Transfer of thermal energy between the system and the surroundings. So this is not a state function. It depends not only on the initial state and the final state, but also the path that's taken between the two of them. Heat absorbed by the system is positive. Heat given off by the system is negative. Okay, heat absorbed by the system is endothermic. Heat given off by the system is exothermic. The change in potential energy U is equal to the heat and the work. So delta U equals Q plus W. All right. The work, sorry, it's going to bug me if I don't fix it. The work is the energy transfer that is used to do something other than changing the temperature. So I'm doing work, but that's not related to changes in temperature. Now that is not a state function either. So it depends on the initial and final state, but also the path taken in between them. Work done by the system on the surroundings is positive. Work done by the system by the system on the surroundings is negative. On the system by the surroundings is positive. There are many types. We can look at mechanical work, which is our physics, our electrical work from redox reactions, or surface work, which is related to our intermolecular forces. Okay. Our mechanical work is really for chemistry described as the expansion and compression of gases. So our work is equal to negative P times the change in volume. So as we look at whether it gets bigger or smaller, that's our change in volume. Okay? Questions, comments, problems about the heat and the work that we talk about for the Syst. Okay? All right. And if you have questions, comments, or problems, you know how to get a hold of me. Email, phone, drop by my office hours, stop by my office, let me know what's going on. We can talk about the enthalpy of chemical reactions. If we keep the volume constant, the change in internal energy is only related to the change in heat. Okay? So delta U equals Q minus P delta V. Since delta V, the volume, is constant, we only have Q or delta U equal to QV, or the heat change at constant volume. Since this is nearly impossible to do, we now define a new function of a system called enthalpy. Enthalpy, H, equals U plus PV, where U is the internal energy, P is the pressure, and V is the volume. These all have energy units. Okay, U, P, and V are all state functions. So delta H is also a state function. Bear with me just a moment, because this should be. Had to fix it, sorry. So U, P, and V are all state functions, and so delta H is a state function. So delta H equals the change in enthalpy equals the change in the internal energy plus the change of the pressure times the volume. And if we hold the pressure constant, we get delta H equals delta U plus P delta V. Okay? Since most chemical reactions are constant pressure, we can equate the following. Delta H equals the H of the products minus the H of the reactants. All right? If delta H is positive, the reaction is endothermic. Heat is absorbed by the system from the surroundings. Heat is a reactant. If delta H is negative, the reaction is exothermic. Heat is released by the system to the surroundings. Heat is a product. In both cases, we can see the effect of Le Chatelier's principle from the heat. Thermochemical equations show both the mass relationships and the enthalpy changes. So, CH4 gas plus 2 O2 gas going to CO2 gas plus 2 H2O gas, delta H equals 88.0 kilojoules per mole. All right. H2O solid going to H2O liquid has a delta H of 6.0 kilojoules per mole. But if I multiply that by 2 H2O has 2H solid going to liquid has a delta H of 12 kilojoules per mole. Okay. H2O liquid going to H2O solid, okay, the reverse of this reaction is the same value, opposite sign. We've seen that before. So these values depend on the physical state and the stoichiometry. All right, so I multiply my equation by 2, then the value of H is doubled. If you reverse the reaction, the value of delta H changes sign. And when I said we can see the effects of Le Chatelier's principle for the heat, if heat is a reactant and the heat is required to get that to happen, if I raise the temperature, then that reaction is going to shift forward. If I raise the temperature and the delta H is given off, heat is a product, then my reaction is going to go backwards. Okay, so that's what I mean by Le Chatelier's principle. So don't forget about that. Okay. Whew. All right. So comparison of delta H and delta U. Well, delta U equals delta H minus P delta V. Since there is work done if the volume changes in reaction, the internal energy and enthalpy are not always equal. The values are similar, but they differ by the amount of work done by the change in volume. So delta U equals delta H minus RT delta N. Since the change in volume in most reactions comes from the change in the number of moles of gas present, we can rewrite our relationship as above to account for the difference in internal energy and enthalpy. So if you're asked to solve for that, you can do it using this. Okay? That's how that works. And this is, and I'll show you this in just a moment. All right? Questions, comments, problems about that? Like, I don't know. I haven't seen it yet. Let me see what it looks like. Okay. Given the following information, calculate the heat evolved when 87.9 grams of SO2 is converted to SO3. So 2 SO2 gas plus O2 gas goes to 2 SO3 gas. Oh, sorry. And the delta H for that is negative 198.2 kilojoules per mole. So if I have 87.9 grams of SO2 and it's 64.07 grams of SO2 per mole of SO2, and there's 2 moles of SO2 in this reaction and 198.2 kilojoules per mole, then that means that this reaction, when I only have 87.9 grams, is negative 136 kilojoules. Okay? If we calculate the change in internal energy when 2 moles of CO2 are converted to 2 moles of CO2 at 1 atmosphere at 25 degrees C, we have 2 CO plus O2 goes to 2 CO2. The delta H for that is negative 566.0 kilojoules per mole. Delta U equals delta H minus RT delta N. Delta N is the moles of product gas minus the moles of reactant gas. On my reactant side, I have 3 moles, 2 and 1, 3. My product is only 2, so my delta N is negative 1. My delta U is then delta H, which is this negative 566.0, minus 8.314 times, or divided by 1,000 to get to kilojoules, times 298, because that's the temperature that we're working at, times negative 1. All right? And that calculates the delta U. So negative 563.5 rather than negative 566. Okay, not a big difference, but that's what we're talking about. All right, so there are 2 takeaways from this. 1, you should be able to tell me what is the amount of heat that we're talking about for a particular amount of material, i.e. convert from grams to moles and then consider how many moles are in the balanced equation. Yay, because that's what we have to do. And then you should be able to tell me, based on what the change in the number of moles, what is the relationship between the internal energy and the enthalpy. Okay? Now, I do not think that this reaction or this relationship right here is in the exam handouts. So if I'm going to ask you to do this, I need to provide you with the relationship. Okay? I don't expect you to remember. Questions, comments, problems? All right. I hope there aren't any, but again, if there are questions, comments, problems, concerns, anything, let me know. Same ways as we always do. Email, phone, office hours, stop by my office. That takes us through our beginnings of thermochemistry. Yay, that was fun. Awesome possum. Again, I will put together some questions for you so you can see what this is going to look like on the third exam. As far as preparation for the final, there is some materials, Unit 1, Unit 2, Unit 3 practice. That is all related to the final because I don't write that. That's a department final, and so that's practice related to the department final. Okay, so if you haven't looked at that, that's what that is for. Okay? All right. So I'm going to bid you adieu for now, and I will talk to you soon. Stop sharing. All right. Thanks, guys. Talk to you later.